Hey, we're going to get started in just a few seconds. Great, so it's my pleasure to introduce Professor Eric Ford from Penn State University for our joint JHU Space Telescope Science Colloquium today. So Professor Ford earned his PhD from Princeton University in 2003. He followed that up with Miller Fellowships at UC Berkeley and then a Hubble Fellowship at the Harvard-Smithsonian Center for Astrophysics. He started out as faculty at the University of Florida, but then he's moved to Penn State, where he has been since that time, and he is now a distinguished professor. So Eric has been awarded many things over his career. The two of the most potentially outstanding are, first of all, the Division of Planetary Sciences Harold C. Urey Prize in 2011, and also the AAS Helen B. Warner Prize for Astronomy in 2012. Today, Eric's going to tell us about the work he and his colleagues are doing to refine the Doppler technique to optimize its ability to detect the lowest mass planets, and what importance that might have for the Habitable Worlds Observatory.
Thank you, Kevin, and everyone for inviting me. It's good to visit some old friends and find some new faces here at Hopkins and Space Telescope. So as Kevin said, I'll get started giving a little bit of an overview of why we should care and why radial velocity should be of interest to the broader exoplanet community. This will be a kind of compilation of many different threads from people working at several different angles. A lot will be results from the NEID team, some collaborations across teams, some collaboration with statisticians. So we want to plan for a future where we're going to characterize Earth-like planets, and the goal stated from the Decadal survey was to characterize 25 potentially habitable planets without defining what a potentially habitable planet was. That might be a good thing because we can adapt it as needed to meet our capabilities, but regardless of how it's defined, it's going to raise a few key questions. First, how big of a space telescope do we need to build? There might be some strong constraints that we'd like to respect, but we want to understand what the limitations of our architecture will be. Where should it look? That's basic of any observation. And when will the planets be visible? For time's sake, I won't really dive into the latter one other than to point out that a lot of the questions we ask here about efficiency only get amplified as you consider the logistics of a mission that has an inner working angle and planets that might only be visible a fraction of the time, really emphasizing the value of knowing when to look where. Okay, so there's the questions we'd like to answer, and that is how common are these potentially habitable planets? And there's the question we can't answer. So what we can do from the current data is how common are Earth-sized planets? This has been done based on data from the Kepler spacecraft, which was really designed with this as one of its primary mission goals. And the good news is we now have data showing that warm Earth to Neptune-sized planets are very common for sun-like stars in the galaxy. And the occurrence rate keeps rising basically as far as we can see. So there's no kind of warning signs that things might turn over to as we get small. And we can give you a rate with a real error bar if we want to ask about Earth-sized planets in the inner solar system. We can argue how far out that should go. Should we say to 100 days, 300 days, 500 days? And basically it's a gradual loss. As you go to longer periods, your error bars and biases increase. So that was the good news. The bad news is, despite Kepler's best efforts, there's very few detections of planets that are really rocky planets in the habitable zone of sun-like stars. And therefore, there's a considerable uncertainty in eta Earth, this rate of potentially habitable planets. You can see this sort of by comparing values in the literature. Here the colored bars. This sort of exaggerates the effects. Some of the early studies were either based on incomplete data sets. Maybe their methodology was still improving as we made progress. But the histograms here give you a sense of, with the final Kepler data set, this is the types of uncertainties that we're dealing with, based purely on the sample size and finite number statistics. In addition to the uncertainty I just showed, there's also the realization that in an analysis you have your prior knowledge, you have your data, you combine them to get your posterior information, and sometimes the data is so great that your posterior doesn't really care as long as your prior doesn't say something is 0 probability. It figures out what the right answer is. And other times when you dive in, you realize that actually your prior matters. So here comparing a pointer, but we have two different models, a uniform prior and a Dirichlet prior on the radius distribution for planets, and those are shown in the dotted lines. And you can see the data clearly provides a strong constraint ruling out the highest rates, regardless of which our prior says. But on the tail towards lower rates, you'll see that it largely is influenced by the choice of prior. And so while we can give you good information about the upper limit, the lower limit is not yet well constrained. And so that means we have a little bit of uncertainty that's about not just the finite number of the data, but also what our prior knowledge we bring to this. There's another effect that our group has sort of specialized in trying to account for, and that is we don't just want to take planets, put them in the numerator, stars put them in the denominator, and take an average. We want to know if I'm looking at a star, what's going to be around that star. And that means if I have a bunch of planets around one stellar system, so I have an average of 5 planets per star, well, the average rate of planets per star and the rate of stars with interesting planets can be wildly different. So what we try to do is to go beyond the independent assumptions to consider models where we take into account the fact that planet formation appears to be correlated, producing similar size and orbital periods around the same star. There's been an evolution of these models as we keep adding more and more factors. The most recent sort of upgrade to this was trying to incorporate simultaneously the clustering of planets within a planetary system and the ability to reproduce the bimodal radius distribution seen from Kepler. And that, in some sense, it's more model dependent. We're putting in models for physical processes that are able to cause this bimodal radius distribution, putting in a smooth mass distribution, letting the radii emerge naturally. So a little more model dependent, but also allows us to capture kind of both the key features at once. And one of the nice things you get out of this is you can see not only where are we today, but you can compare the hollowed out dots were the initial size of the planets, and the red dots are where they ended up. And you can see at some radii there's a mixture of planets that still have largely their original radii, some that fell onto the rocky worlds, other places where they almost certainly would have lost their atmospheres, and today we'd see them in a rocky configuration. So this can give you insights into, well, if I want to know what should HWO look at, and all I have now is its radius, at some radii it's very likely to be have a modest atmosphere. At other radii it's very likely that the things you see will be dominated by gas rather than seeing to their surface. So that gives us some quantitative ideas of what radii we should be looking for. And this upgrade also allowed us to reproduce the bimodal radius period distribution seen from Kepler. So that's really nice progress, trying to get the most we can out of Kepler to understand these factors that affect both the measurements of Eta Earth, but also the planetary systems that will be important for figuring out where the planets are in that system and how our knowledge about one planet affects the other planets in the system. So now we can do conditional occurrence rates. If I know the system has this type of planet, what do I know about the additional planets interior to, say, an AU or so? Okay, so we have that Eta Earth is unknown. We can give a best estimate of the rate. One interesting thing is that between the models that did not account for the bimodal mass radius and ones that did, we saw Eta Earth actually decrease significantly. So these choices, which at some point we're putting in different prior information, we can see do have meaningful changes on the rate of Eta Earth, and that translates directly into either the size or the observing time that would need to be devoted for a survey from Habitable Worlds Observer. So we saw there's uncertainties to a small sample size. Lower limits are sensitive to model assumptions, particularly when we get to larger orbital periods. We have low sensitivity for the planets to give a firm upper limit. And there's some more complications outlined pretty nicely in two recent review type articles by Steve Bryson and Rachel Fernandez. One more factor I'll put in to kind of combine things, that these aren't, the models are a little bit different, but the directionality is right. One possibility is you can look at, let's imagine we knew what Eta Earth was exactly, but we took into account that we're looking at a small volume. We're not interested in the average value. We're interested in the value realized for a finite sample of stars. And so for the sample that HW looks at, there's a width just due to the fact that we're going to pick a small sample size. If you convolve that with, in this paper's one approximation for the uncertain Eta Earth, you can see it gets even broader. And at least our baseline mission that was considered in the paper by Stark et al. Here, you can see there's a pretty broad distribution in that rate of expected yields from a baseline survey. So what that tells me is if we want to realize good science from this, it would be a humongous advantage if instead of starting with a blind survey, if we could start with a target list. Not a shocking conclusion, but it really emphasizes this isn't just a nicety, but could be transformative in terms of the potential of making Habitable Worlds Observer have the time to do the characterization of a large number of planets, and also available for general astrophysics, assuming you let the planets take as much time as you want has negative consequences, so we don't want to do that. We want to know where to look. Okay, so where should we look? One thing you can do is you can just take the nearby stars and kind of plot it out. And this is, again, one particular example of a realization of a mission. And you can see that for a lot of the targets, you have a pretty good completeness. But as you go further and further away, the completeness drops and drops. And again, this means the expense gets really expensive as you try to go to these larger separations. Not only do you have the ability to detect a planet if it's currently outside the inner working angle, you also have the challenge of if you don't know when to look, it'll be outside the inner working angle a smaller fraction of the time, so you have to go back more often to rule out planets in their habitable zone. And so we really want to be able to have a targeted survey where you know when the planets are at maximum separation and which ones are worth studying. With this in mind, back in 2019 or so, NASA-NSF put together a joint extremely precise radial velocity working group to kind of lay out what would be required to make this work. What type of, we call them architectures, configurations, were plausible scenarios to be able to provide the sort of work for Habitable Worlds Observer, using the Doppler technique as the tool to get there. And after a lot of discussions and calculations, basically they conclude a lot of different architectures could work in the sense of you could collect the photons you needed to be able to measure enough radial velocities to do a survey to find some targets. Here you can see that the wide variety of things considered, everything from kind of ridiculously large architectures, combinations of ELTs and KEKs, and hundreds of small telescopes. And there were some preferences, but in some sense the thing the working group considered was really based on a photon-limited imagination of what would it take, just assuming we have get the data we need to measure a simple Doppler shift. The challenge is we could basically put in photon noise as a function of the telescopes we put in. We could put in the current status of the instruments, and then we had the kind of this wild card for the effect of stellar variability, and we said, well, let's assume that problem gets solved for this report. And it allowed us to produce a report, just before the COVID break hit. It was my last meeting, so it was maybe good timing. We didn't aim to be too ambitious, but of course we were aware that there's several challenges that had not been addressed. So we had to have a pretty good strategy. So P modes have a short time scale. They're relatively easy to average over. Activity cycles are so long. They're probably a nuisance, but probably not a killer for the longest, for the planets in the habitable zone will be much less than activity cycle for most sun-like stars. And so the region we're kind of most concerned about are these either rotationally modulated features over the course of rotation from magnetic activity cycles down to granulation, supergranulation, the many convective cells rising up and falling down, to first order averaging out, but to second order it's more complicated and an imprinting on the spectrum. So one of the first things after that we did was with Jacob Loon looking at, well, what's the effect of accounting for these correlated noise signals on the architectures considered, and realized that some architectures actually are a better fit than others. So before we might have said you could get away with having a small number of 8-meter telescopes and do what you need to do, and we found actually that same architecture, the fraction of the time you would detect the planets plummeted once you accounted for things like granulation and supergranulation causing correlated noise from night to night, and you're actually better operating on a larger number of more modest-sized telescopes. It did drive up the overall observing time required, so mainly we said, okay, maybe a 5-year survey wasn't such a good idea. 10, 15 years seems like we could still be there, so helping us to put it in perspective, if we deal with a stellar activity signal where we assume that we are able to suppress it but not kill the time variability, and we try to overcome that with resolving the temporal behavior, how much would it hurt us? And so we're able to see it doesn't put it out of the question, but it does drive up the number of observations, and therefore either number of telescopes or survey duration. 15 years is annoying for a graduate student. 2026 plus 15, early 2040s, right? So if you want to launch in 2040s, this means you are making nearly all your decisions before you have the target list. Not the ideal situation, but maybe by the time you added some mission delays, maybe it all works out just right. So on one hand, we're not in a desperate situation yet, but we do need to make progress soon if we want to be able to implement this on a time scale that can really inform mission design choices. So we've gone from a world of photon limits to stellar activity limiting the capabilities of radial velocity surveys. And so when you change that model of what are you doing when you're looking for planets, it can affect how you think of things, right? So if I think of a photon noise dominated world, I might be thinking, okay, well, when I say radial velocity, the center of the mass of the star is moving, I have a real physical understanding of what's happening. The spectrum should shift exactly, and I can write that down, do a Taylor expansion, everything's great. But once I say, well, actually what I'm doing is I'm mostly modeling stellar activity, and I'm looking for a residual in the stellar activity due to a shift, well, now the first order signal is something I don't have a physical model for. This almost transitions us from the world of physics and nice mathematics to the world of the kind of softer sciences where you don't really have a model for how people behave, but you put something in your code that does something, but you can't trust it exactly. And do I want to right? So it's a different mindset once you're at the point where your primary signal is something where you don't have a fundamental physical model. And so that's a difference in the types of approaches you want to take to the problem. When you have a world where everything can be described by the mass, the same major axis, Kepler's laws, you only need a few parameters. But once you say, well, actually, I'm modeling 3D MHD with radiative transfer, I can make a statistical model, but the number of parameters explodes. So how does this affect the ability of a survey with a finite number of observations to do a reliable inference? And so it really does change the game a lot in terms of what are you aiming for. And it will probably also shift from where before most of the discoveries were based on large signals compared to our noise. Now we're typically going to be looking for discoveries that have a signature that's comparable or even less than the dominant variability source being the star itself. Astronomers are a clever bunch. They try lots of great ideas, and this project led by Li Zhao, Express Solar Signals Project, they provided some nice Express data sets. Express is one of the new generation of instruments at the Discovery Channel telescope on several stars, and they had different groups try to analyze the data. And on one hand, every group said, I have a fancy method that can help. On the other hand, when you ask them, well, what do you predict happened on February 18th? And they didn't always agree on the sign, let alone the numbers, right? And so we realized, okay, well, on one hand, we can certainly improve our signal to noise in some sense if we fit a model, but how are we going to distinguish between what's actually we should trust and what is playing with computers and numbers? And so as we go into this data-driven world of trying to explain complicated systems, we sort of have to back up and learn some of the early lessons. You might have seen examples of kind of hilarious failures where you get, okay, we'll have a lot of images on the internet. We can label them red fire hydrant and yellow fire hydrant. If you give it very similar things, easy to do very well here. But inevitably, sometimes you encounter it's not exactly what you expect. How is it going to about green? Well, okay, maybe you'll say yellow. But I guess actually the cap kind of looks more like the red one. And so we don't want this to be, this isn't science, right? This is playing with models for fun. And so how are we going to take it beyond that? So we really have a fundamental question of, when we've gone from a physics-based model to a data-driven model, how are we going to develop and then validate these models so that they can be trusted to make large value decisions about where to spend time from Habitable Worlds Observer? So one of the tools we're going to try to do that is this beautiful picture of the WIYN Observatory, and there's the telescope of interest. That is a teeny little solar feed about this big, which is going to look at the sun. Right, so every night, of course, we hope every night, but most nights, where there's good weather, NEID will get on sky if it's not a night where other instrument says all night for some reason. But every day, regardless of what instrument is on at nighttime, if it's not terribly cloudy, the solar telescope can collect data, and that has some nice properties, right? So on one hand, we typically might take one, maybe 3 spectra of a star a night. We can take 200 spectra of the sun every day. So each spectra isn't actually that different because we have to throw away most of the light to not saturate detectors. But 2 orders of magnitude more data for the sun than for other stars. We have no competition for other things to observe. We have similar durations and great sampling. But really the key difference is we know the velocity of the sun. So for once, we have a realization of this complicated physics that we're kind of scared of, where we know the truth and we can ask, okay, will your models be able to accurately recover this? If you just do the simplest thing of running through the solar data through a pipeline developed for nighttime stars without doing any corrections for kind of solar peculiarities, here we have kind of 3 runs. We picked one before there was a fire that caused a shutdown and major distraction. After the fire, then there was an Edeline upgrade due to some instrumental things. Each of those, you can see pretty clearly the rotational behavior around solar max. It's nice and big. We're fortunate to get this guy just in time while the sun was still just about to bounce up. And so you can see that even for the sun during solar minimum, you can see 2 meters per second of scattered night to night, sometimes 10 meters over the course of a month. Right? 10 meters per second is 10,000 times bigger than 100 times bigger than the 10 centimeters per second signal we want to look for Earth. So that's the challenge we're going to have to be faced, is how do we find a signal orders of magnitude less than our distractor. So one thing that's come of this is by virtue of having a high cadence of observations, we can begin to study things like granulation, where there's correlated time behavior of this pattern of convective cells rising and falling across the star, and compare that to photon noise, right? So in the idealized world, you have a 1/√n improvement as you increase the number of observations. Reality is not so nice. We use this to then develop and fit models describing the behavior of the granulation signal. And at this point, I'd say we can quantify the effect of granulation quite well, and the next step is to be able to see if we can remove it. We now actually have several solar telescopes working in parallel. There's one at HARPS North, the original one. Here I show NEID and Express that I've mentioned already. Also, HARPS in South has one, as does Keck Planet Finder on Hawaii. So there's several solar telescopes in regular operation, providing nice data sets, and we can start to compare them. And so the good thing is, we can see that these instruments there's some heritage that's shared, but there's different instrument teams, lots of things could have gone differently. And even like the wavelength ranges covered, so the lines being used differ from instrument to instrument. So even like the first order question, how well they agree, was not clear how they do. Here are the different color points of the different instruments. You can see, time-wise, you start in Tenerife before you get to Arizona over here. But there's enough overlap we can kind of piece them together. And one thing you'll see is, not only is there something over the course of months that is what we were aware of to be concerned of, but these little fluctuations over the course of an hour that you might have thought like, well, I don't know, maybe your instrument, and that's not the instrument, that's the star, right? We can see it, different instruments, different sites, different telescopes. So there's short-term variability at the meter per second level over, say, an hour. And the bad thing with that is, it's not practical to resolve that in time. You can't just sample once a day and see the pattern over the course of a few weeks. If you're only going to observe each star once per night, you're going to get that snapshot, and maybe it's high, maybe it's low. What are you going to do? So that really motivates us to try to go beyond methods that are going to use the temporal variability of things like fitting correlated noise models, Gaussian process models for the quasi-periodic behavior of the stars, and to shift looking into what I call the wavelength domain. So trying to see from an individual spectrum itself, without knowing what happened the day before or the after, can I figure out how much this star's velocity was perturbed by whatever the sun happens to be doing that day. So what sort of information can we have to work with here? Here I showed a kind of toy model of a spectral line. We can draw a bisector, just literally picking a depth, drawing a line halfway in the middle. And then we'll consider this object of interest. The velocity scale here would be kilometers per second. Let's now zoom in to hundreds of meters per second. And there we might have a line with some little wiggles. There's some photon noise in there. And then we play that over the course of, say, 20 minutes. And so this is what's happening to that line. This actually has the P modes removed. So that's not your P mode. That's a granulation signature. So what this says is that spectral line that we imagined as a wholesale shift left and right, there's some shifting left and right, and there's also some shape changes. And can we use the shape changes to recognize how much the bulk shift is occurring as well to remove that signal? And so that's kind of one of the challenges we have. There's another way we could try to solve this, and that is we don't just have one spectral line. Typically, you might use 4,000 spectral lines for a solar-type star, and the usual process, we average them all together. But we can also look at individual spectral lines now. We have so much signal-to-noise for the sun, we can measure one line to a few meters per second, and you can see that some lines look like a nice, well-behaved line. This depth, sorry, top line. Radial velocity here. And others, oh, this one I don't know, something this day this month had a big little shoot up over there. This other line here kind of a long-term trend. And this one, the time is going down, and that one's going up. So it's not the textbook story of the spectrum shifts. We have thousands of different ways to measure the shift that are doing different things. And those differential behaviors of different lines is additional information that can probe the atmosphere at different heights and the ability to try to figure out what's really happening on center of mass motions. And so this sort of inspired us to rethink the way a pipeline works. So traditionally, we take one CCD detector's image worth, and every one of these exposures becomes one data point, 3 numbers: time, velocity, sigma. Right? And that's the entire reduction. That was great in the photon starred regime. We were trying to get as many, as high precision as we could from a relatively low signal to noise spectrum and adding all the lines together, averaging them up. But now we're saying, well, we might need that information across the different lines to be able to solve the stellar component. We don't want to average everything together first. So instead of going from early steps of extracting a spectrum, normalizing, and then early on we would typically average all the lines together, we're going to, and then we have like our kind of average lines. That's what we usually work from. So I'll talk about 2 methods today a little bit. One is to use the shape of this kind of average line, the output of the cross-correlation function of the spectrum with some sort of mask. The other is we can then start breaking that up into many different kind of lines averaged over multiple groups, or we could go all the way back to every individual line, and then all the way to the shapes of every individual line. So where on the spectrum should we fall? We kind of have said the old paradigm of going all the way to the end in one jump may not be preserving all the information we want. Is there a way we can go deeper by using some intermediate level data product here, the intermediate level of data reduction? And so that's the opportunity is to try several different ways and see how they do. So what are some extracted features you might add in addition to the radial velocities? So the early efforts were based on things astronomers have been measuring for decades, things like the emission in the core of the calcium line. We kind of know it's correlated with magnetic activity, but there was no motivation for this to be a probe of the perturbation to radial velocity. It's just something people have been measuring because they've been measuring it. And so maybe not the best thing to correlate with. Maybe we can make something that's astrophysically motivated. I showed the bisectors before. You could try to get summary statistics for them, maybe comparing velocities measured from different subsets of lines. Or you could go kind of the whole data-driven approach of like, let's just find ways to parameterize our whole spectrum in terms of different bases. Maybe we could use Fourier decompositions or Gauss-Hermite functions or some sort of other method that we're able to remove the Doppler shifts, make them shift invariant, measure shape properties of the lines, use those shape properties to then pull out what's left. So how well can we mitigate the stellar variability in the spectral domain? So not using the time information from one spectra, given there might be a small perturbation that we don't know about from our time information, how we can see in one spectrum. And so we tried lots of things. So some of the early methods trying these classical activity indicators make a big difference, right? You can go from maybe 2.5 meters per second to 1.5 meters per second just using classical activity indicators. That's good. And then we kind of take that idea and say, what if we play with some of these other astrophysically motivated shape parameters, things like bisector widths and curvatures, and maybe make a little bit more progress. And then we go to some of these more data-driven methods, have more flexibility, the ability to figure out what is it that's able to correlate with it. And different methods have different performances. So here just 4 different things my group happened to try, and you can see all of them helped. One happened to do particularly well, and we got pretty excited about in terms of how well with this method it's able to use the autocorrelation function, the CCF. So we are averaging all the lines at this point, but using some information of the shape of that in a nonlinear way. Nice improvement. Still not at 10 centimeters per second, but a nice step in the right direction. Now the downside of that is that was based on observing the sun for 200 observations a day, several hours. That might not translate so well to nighttime observations where you might want 15 minutes of observations. And so we want to see what's the signal to noise necessary. And so here we kind of play the game. We're like, well, we can not average over all the data, average a little less. And you can see that we kind of have almost plateaued. And there's a photon noise limited regime, and then we kind of transition off here. So on one hand, this break here occurs like it's annoying. Like, half an hour is a lot worse than 15 minutes, but an hour isn't infeasible, right? We could do an hour if we really needed to. It has a cost, but it's a you know, it's a marginal cost as opposed to a don't try me type scenario. So on one hand, I would say the current methods are able to do very well on the sun. We have no reason to think that they wouldn't work for other stars. We haven't demonstrated they would, and so that'd be nice to do. We currently have a program studying one K-star, trying to get that level of precision to see if we're be able to mitigate that star's variability as well as the sun. But it does sort of ask the question of, well, currently, the methods we have are predicated on getting very high signal-to-noise to measure these higher order shape features. So the ones that are kind of in the can and we could use are saying we have the ability to get within stone's throw of this 10 centimeters per second distance using methods at high signal-to-noise, but that's going to have a very high cost in terms of either the number of telescopes you build, the number of targets that would be practical for Habitable Worlds Observer, and could we do something to make progress there? So if we go back to this spectrum of different analysis methods, one thing we haven't tried yet is going to these using information for individual lines. So on one hand, great, we don't have to bother with all the pre-processing steps. We can just go look at each line individually. The bad thing is now, instead of having a time series of one scalar versus time with one error bar, if you have 2,000 lines, you measure 10 shape parameters for every line, you now have a 100,000 or 10,000 dimensional time series. And doing inference on that is not obvious how you would convince yourself that you found something, how you would be able to do practical computations on it. So I've been working with statisticians, Jesse Szewski and Jeff Salzer here at Wisconsin, on developing methods that were able to use line-by-line shape information in a computationally practical way. One of the first questions you might ask is, well, how many lines do we really need? And so I like this figure because it kind of helps us understand where information is coming from. So what I do here is we pick 2,000-ish good lines, and we say, let's use them all, and then look at how much variability is if we were to use that set of lines for measuring our velocities. And then these different curves, let's take a line away. So maybe I'll start with the purple curve here. Kind of under the green, I guess, but follow my finger. If I take away the lowest signal-to-noise line, the next lowest signal in the line, right, and I keep going down, you can see that, yeah, I lose, but I don't lose much. And we're able to do just as well using a few hundred lines as opposed to several thousand lines. So evidently, most of our information is coming from those, but just using the high signal-to-noise lines isn't improving things. It's just not getting worse. On the other hand, if I look at things like, well, how does the velocity of this line show correlated noise on a rotational timescale? And I say, let's take the one that's the highest noise that timescale, take it out, and drop those. Well, pretty quickly, a few hundred lines are gone. We've already made a substantial decrease in the uncertainty of each observation. So there's a subset of lines, hundreds of lines, that even just do the simple thing of just taking their average does better than taking all the lines. Right, okay, so evidently boosting our photon noise wasn't the best strategy. The best strategy is to find the lines that behave well. And you might first think, I want to find the quietest lines, and we probably do. But then you also might think, can I find lines that do opposite things? And I can use variables that are anti-correlate with each other in order to get a more sensitive measure of the activity from the lines that vary more significantly. And so that's where you start wanting to be able to find, how are we going to put this into a model where we can use the information both from the quiet lines and the active lines to help us suppress the signal from those 1,000-something lines that evidently were kind of a distraction if you only want the signal, but they might have extra information that we need to exploit. And so I always like to start simple. So we started with what's known as a linear effects model. So we're literally saying the velocity we measure for each line at each time has something that depends on time, has something that depends on the line, and then has an interaction term. So we can put in information about the shape of that line, different features. Maybe it's expansion in terms of Gaussian fit, or Gauss-Hermite polynomials, or principal components, some sort of statistics describing how that line behaves, and then we can try to fit for those to improve the precision of our final velocity estimates. And you can see what happens here. Our blue is kind of our baseline model here. We pruned the data a little bit to bring it down already. But then for those, you can then see after applying this linear model, dramatically bring down the RMS now back down to about 40 centimeters per second. You can still see the rotation period, right? I mean, where it's varying before. So it's not gone completely, but dramatic improvement in the distribution of residuals there from this linear model. So that gives us some confidence that we're going the right direction. And there's two directions we could go. We could try to optimize the number number. So I could say, well, I assumed linear model. Before we saw nonlinear model helped a lot more using line shape. So maybe that's going to be a direction that gets us to a better precision. Alternatively, maybe we should go in the direction of trying to simplify the model. At this point, we're up to tens of thousands of model parameters, and there's always a kind of challenge in the interpretability and explainability of that and robustness of it. So we'll be thinking about how we'll be able to exploit the model we have, maybe push it further, but also not entirely focus on one number, but rather think about what would it take to establish confidence in a detection, and what would we like to understand it. So within this model, we can ask, okay, well, so we fit to say how much it should use every line's information. There's a little bit of subtleties that each line has not just a velocity, but also other shape things. But here we give a sense of like how much weight each line is getting. And so on the bottom, we have line depth. On the vertical axis, signal to noise. So if it were just a matter of photon limited, right, then you'd say, oh, let's give the highest weight to all the things the highest signal to noise, give the lowest weights to the things that are lowest signal to noise, they have the least information in them, and so we'd kind of see a color contrast of shades going from dark blue at the top to yellow at the bottom. Instead, what we see is that there's a subset of our deepest lines that give us the most information. Not all deep lines. Some deep lines, I mean, maybe you're not surprised if it happens to be a part of the spectrograph where there's low signal to noise, it has low information. But even in this corner of deep and high signal to noise, there's a significant difference, factors of 2, in how much weight those lines are getting. And as you go further towards the intermediate lines, now you see the biggest range in terms of the information content of that line. And then as you go the shallowest lines, they rarely have so much signal to noise. You want to give them a big weight, but there are a lot more of them. And so collectively, they can contribute a significant amount. And so this helps us kind of get a sense of, again, the number of lines we want to use, and also we can see there is a correlation with line depth, but it's not a simple one. There's something else going on. And we tried being clever, astrophysicists, we looked at, excitation potential and line species, and we wanted to understand, oh, we just need to do these 3 groups. And despite trying, we basically came with nothing that was useful, right? There's a little bit of correlation with line depth. There's a little bit of correlation with color, a little bit with signal to noise, but nothing approached the quality of the results coming from these data-driven methods. And so then we're like, okay, well, if we can't predict groups of lines that would be really useful to use, could we do something where we instead look to find lines that behave similarly in a data-driven fashion? And so Kanish Pandey is a grad student working now to develop methods to find groups of lines that behave similarly. So here we have a spectral line just indexed, so just sorting the lines roughly blue to red. It's a little bit, it's not quite in order, but basically blue to red. And then time, showing several different time epochs. And some things like, okay, here's a red band. This means it looks like the star shifted in most of the lines. And so that would be the stellar activity contamination. But we can see it's not as simple as all lines do exactly the same things, but rather you can see there's some of these groups here. Oh, sorry, I was wrong. This is resorted. So the different color bands here, we've sorted for different groups of lines that behave a little differently. Some are very small. The small number of lines have one pattern. There's like here, a little narrative there. And other ones are quite large. We can see a lot of lines have a similar pattern of the magnitude of the effects at different times. Then we go, okay, let's take those. And maybe we don't want to use every little group. There's probably some minimum amount of information we need to be able to extract information in a real life setting. So we can kind of prune them and only keep the lines within a group that are highly correlated with its own group, and also only the groups that are large enough. And so then I sort of boil it down. And maybe here you can see a little better. Some of these groups of lines respond quite differently to the same activity where another group responds well. So now we have data-driven choices for groups of lines that show similar, in this case, depths of the lines varying in the same way. So now instead of taking all our lines and averaging them all together and then just trying to make a shift of one average line, well, now we could group 10 different groups of lines. For each of those groups, look at its behavior, and then try to build the signal to noise across many lines and look for what's going on there. Okay, so maybe this will be a little bit more interpretable to have a handful of groups of lines as opposed to 1,000 lines all doing different things. But can we get a sense of why they're behaving differently? So here we picked a couple examples where we look at the radial velocity and the calcium index for an observation. And for each line, there's a point showing where this velocity and calcium index go together. You see a fairly strong correlation, but a lot of scatter. If I just take all the lines within, there's the pre-fire data. If, on the other hand, I take out some of the lines that don't belong to any cluster, still a similar level of scatter, still a similar level of correlation. But I look at, say, one cluster. Well, this cluster here corresponds to a narrow range of velocity, so it's less sensitive, and seems to not care what my calcium index is, which days high activity, low magnetic activity. They're giving a very similar velocity. So we have a cluster that's less sensitive to magnetic activity. And we can also look here I'm looking at the auto correlation function as a function of lag. So by definition, at 0 days, it goes to 1. As we do a day, 2 days, 3 days, you can start to see it's correlated night to night. By the time you're maybe a quarter rotation, it starts to get anti-correlated, come up to a rotation period. There's a little peak. Some active regions last long enough. And we can compare, well, if this line didn't know about activity, then of course we'd expect it to be flat at 0. That's not what's happening. Both the all lines and this particular cluster both show activity signals. It's a little bit suppressed. But perhaps the biggest difference here is actually over here, 365 days. We tried to clean the line list of tellurics. We knew where all the tellurics were. We said if it's deeper than this, within so far, cross that line off. Don't look at all the lines. Only look at the ones that should be telluric-free. Evidently, we didn't do a very good job because we found this cluster of lines that's among our best ones, and yet you can see that, oh no, this is good. So the best ones show basically 0 correlation at a year because they've been cleaned very well, but the overall population contains some lines that still are having some contamination from some sort of telluric feature, probably some blends passing into and outside of the stellar lines being used. And so here we can see 2 things happening for this one cluster, both less correlation at the rotational period and then basically 0 correlation on a telluric time scale. So we can start to dive into each of these clusters individually to understand maybe not what is causing them, but rather what effects do they display, what types of processes are affecting them. And then so the next thing we can do is say, okay, well, let's imagine looking at the various properties of these and try to understand how these different clusters behave. So here I picked, on the top we have for all the lines in our model, the wavelength, the depths, and the pixel number of the detector. So there's a bunch of orders, and the very edges are where the blaze function is falling off to 0. You can imagine maybe the calibration isn't quite as good. And you can see a lot of lines in the blue, not too many in the red because the filtering for tellurics removed most of them. And we can kind of see what's happening with all lines. Then we can look at any individual cluster and see, okay, well, these basically follow the overall distribution. Maybe this one disfavors shallow lines. This one has, this disfavors the lines at one edge of the detector, the blue edge. But over here we have some that actually this cluster, if anything, it kind of picks up near the edges, right, where it has more lines near those edges. Here we have the ones that kind of favor the deepest lines. Here, disfavor the deepest lines going for shallow lines. So different clusters are picking out different sets of lines in terms of detector location, perhaps telling us about instrumental issues, and depth, probably telling us about astrophysical issues. And we can compare the behavior of those different clusters. So what do we see there? If we take the number of lines in our cluster, so here a similar plot as before, we start with all our lines and we gradually remove them, and we can compare what we'd get from like randomly removing lines is that the contours are showing like random. So if our points fall within the blue shade region, it says we're not really sure the difference here is anything more than just picking random subsets of lines. But when they fall outside these, we're saying the difference in the behavior of this cluster of lines is statistically significant compared to if we had chosen random sets of lines. And we can look at several different features. So first, maybe the most obvious, let's look at the RMS scatter of the lines. So some clusters are more sensitive to some sort of systematic challenge, whether it be activity or tellurics. One cluster in this case was less sensitive. Why is it less sensitive, right? So then we can look at, in this case, the correlation with calcium, so we can understand that the green and the magenta points there have roughly similar but opposite signs correlation with the calcium index. So some lines seem to have radial velocities that increase, others have lines decrease. But then that gray point here, its correlation is pretty near 0. So this cluster of lines appears to be relatively insensitive to magnetic activity. And of course, we discussed there's many different types of activity, so it doesn't solve everything, but at least one of the large processes affecting our observations appears to be dramatically suppressed there. And we can do similar things. I showed you before the autocorrelation functions on different time scales. Here, instead of showing you as a function of the lag, I've picked 2 lags in particular, and we can look at and see things like, okay, well, actually, they all still show a significant correlation at this roughly 28-day rotational timescale. So we're suppressing it significantly, but we're not eliminating it. There's still room to go there. On the telluric front, some groups of lines appear to have effectively suppressed it very well. Other groups still have some telluric type signals. So we're beginning to start to understand not necessarily the microphysics of the Ys, but the macrophysics of what are the properties of the groups of lines that are useful for decorrelating our stellar activity signals from the Doppler shifts imposed by planets, and beginning to try to turn those into powerful tools for finding planets. So if I back up, the three critical questions: how large of a space telescope we build? Basically, we don't know, but for the moment, we'll go with what the engineers tell us they want to build and see what it can do. Where should it look? For the moment, we don't know. We would hope that we'll be able to carry out a survey to find them in time, and maybe we need to start soon. And the final point is, when will they be visible? And so this really gets to this issue of kind of efficiency of your survey. As you go further to further physical distances, your inner working angle gets larger and larger fraction of the habitable zone, and so there'll be a bit of a challenge. So we hope that the abundance will be high enough we'll be able to have study them for extended periods of time to get spectra, but from a detection point of view, it's another reason it'd be really helpful if we had a survey that already knew where to look. So I'll wrap up. On one hand, the success of radial velocity surveys would be transformative for the capabilities of Habitable Worlds Observer. Being able to start with known targets to look at and begin with would be humongous advantage to beginning a multi-year survey, and that would therefore increase its value for the exoplanet community, and also mean that there's a lot more time to do general astrophysics. The current state of the world is that we have tools that are able to do quite well for the sun. So I would say we're within shooting distance of being able to discover an Earth analog around the sun. The challenge is, how well will that generalize other stars? And the real answer is we don't know yet. We're beginning to test these out on other stars, and we'll see if those methods scale well, or if they need, we have, at this point, 3 different methods that each seem to do pretty well, comparably well in the sun. Which of those will do well in other stars? And so part of the reason to develop multiple methods is to cross-check and build confidence that the methods are doing the same thing, but also it may be that some are more customized, tuned precisely for the sun. Hopefully, by reducing the number of parameters, we'll build methods that are more general and able to work for a larger set of stars. Some of the new strategies for mitigating stellar variability have improved by over a factor of 10 in the last decade. So we've made some considerable progress. We still have maybe a factor of 3-ish to go before you'd have the precision you want for having a plot you could see by eye your signals. You can argue, if we really do have the residuals, having removed the noise signals in time, it may be that you can make use of root n to beat on things. It's not quite the same game as the traditional radial velocity. Like, it would be okay if we found a planet and had 90% confidence, because you could go look at it, see the dot. We don't need to make it 10 to the minus 5 false alarm probability when you're going to look at it and see it take a spectrum anyway. So we're not quite in the same regime where we need to establish, without a doubt the planet is there. We do need to boost it from, whatever eta Earth is to 90-something%. And so with that goal in mind, I think we're very close to be able to doing that for true solar twins. And so we hope that some of these promising avenues that we're beginning to feel out with the sun and see where they go will prove practical for other stars. With that, begin questions. Yeah.
Great, thank you, Eric. Any questions from the audience?
Thank you so much for the tour of things that I am blissfully unaware of until now. A question about the kind of third point there. I'm a galaxies person, so very naive. When you take account of solar zone of exclusion, micrometeorite zone of avoidance, flying backwards, day side, night side, etc., like, even if you know where to look, what fraction of the year, what fraction of the Habitable Worlds mission will a given Earth-like planet be visible for on average?
Good question. I'm not the person to ask for that, so I don't have a real answer for you. I know was it Rhonda Morgan might have done some mission planning simulations where she was looking at taking into account these logistical, practical complications and to what extent they affected things. So there's at least one paper that's looked at those sorts of things, but I'd have to look it up to give you a real number. It may depend on where you are. I mean, traditionally the ground-based surveys like to pick stars that are visible a large fraction of their year, right? So, but that's kind of the almost opposite of like what presumably the viewing angle of a space telescope would favor. So it may be that the complementarity of the ground-based surveys and the missions aren't exactly aligned, but I suspect that the bigger issue will be if you have a planet, say its maximum extent is 1 AU, and your inner working angle is half an AU, your orbit is going to spend sort of 60% of its time inside that inner working angle. So I'm more worried about if we can't look at the closest 30 stars, but have to go to the closest 90 stars, then that fraction of time where each star is a large enough angular separation to see its planet gets smaller and smaller. And so I think that will be the limiting factor on how often you can observe the star rather than your very important practical considerations of safety of the instruments.
There is a recent paper by Corey Spahn from Goddard like a few months ago that looked
great
both at the field of regard, but also when you're talking about like if the field of regard is too small, then you just can't catch them when they're at maximum elongation and you don't see them.
Do you remember the headline number from that? It's fine. Yeah, we can follow up if you want.
But we can look it up. Yeah.
Eric, thanks. That was a great talk. So I was thinking about what's after the stellar variability, and I imagine at some point you're going to bump into planetary variability. And I was kind of curious, like, how far away we are from a distant dream on the horizon, or is it soon? And maybe optimistic.
So are you worried about the scattered light from the planet, or something else?
Like the planet being intrinsically variable.
So for the radial velocity technique, we're assuming we see starlight and zero planet light. Are you worried about the planetary light contamination, or?
Yeah, okay. Eventually. Or is this like you need some enormous telescope, I guess?
I think I'd be more worried about there's, say, a giant planet around the same star that might have a phase curve and do something weird. Because surface area of, we're barely detecting the Earth mass planet in the direct imaging thing. For that's not on my radar. I'll put it that way. Okay. It's probably intellectually fulfilling to explore what that ratio would be. I think there are other issues that you can worry about. So, for example, the magnetic cycle of the sun. I kind of said, it's a longer time scale, right? Well, is that for all stars, right? Or are there stars where the magnetic cycle might only be a few years, and then is it that different from the habitable zone? And so I think there certainly are many things you can worry about if you want to dig into the complications. Another one that might be of concern is the planetary variability in the direct imaging game. So after radial velocity identifies, you hand it to Habitable Worlds. So if the albedo is constant, then your goal, then you just fine, wait till it's outside the inner working angle. If we have a scenario where there's substantial variability in its albedo, and you not only need to have the right viewing geometry, but also have to have the right cloud pattern, like that could be order of magnitude effect in its contrast with the host star. So there could be some pretty big issues on that front as well.
Thanks. Eric?
Yeah, thanks for a really interesting talk. So one thing I didn't hear you mention is photometric light curves. Do those provide you with any useful information, or is it just not too broad?
Yeah, you would think so. I mean, like we have these beautiful light curves from Kepler and TESS. So what I can tell you is what people actually did. So when Lily Zhao ran the Express Stellar Signals Challenge, she dutifully provided test light curves for each of the targets, and packaged them up and wrote documentation for them, and every group ignored them. So, I mean, okay, we were all pressured for time. None of us had funding to actually do this. So a little bit of a human limitations, right? But there's also an element of the light curves are probably good for things like establishing what is the overall level of variability, maybe what is the rotation period. I could easily imagine putting into my analysis, I see in the photometry this star has a rotation period of about 30 to 35 days. Let me, when I do my clustering of lines, look for signals at 30 to 35 days. So I can imagine ways we could use it. But the integrated light over the entire spectrum, I'm trying to break up the spectrum into more and more information, and that's compressing it along the one dimension I have. So I suspect it will play information in maybe the target selection and prioritization phase. Maybe you can get some densities from astroseismology or something to pick ones that are less of granulation or something. So there may be in the target selection phase and maybe in some of the design of the metrics to be used in the non-parametric ways. But at the end of the day, I don't think that's going to be a substitute for the spectral information.
So there's a question from the WebEx chat. So I'm just going to read it out. So how dependent is your mitigation of stellar activity on wavelength coverage? And are there certain wavelength regimes that are more or less useful?
Yeah, okay, so I was optimistic. The new generation of instruments, the main thing that distinguishes them compared to the previous ones are they're very well stabilized. So the early instruments, they were sort of stabilized, but not to the millikelvin, millitorr, whatever the pressure units are. Like they've been really paranoid at building buildings for the vacuum chamber, right? So the stability is the main thing that differentiates the new generation of instruments. And that gives you things like LSF stability that allows you to measure shapes and compare them. Different instruments make different choices. So KPF said, let's focus on getting lots of photons because that will be our, pathway to success. Express said, let's focus on getting some higher resolution. We'll, tweak the gradient a little bit angle to get 140K instead of 120K or something. And NEID said, well, what if we try to get a large dynamic range? We can go all the way from calcium out to, I have photons at 1.1 microns, not a lot, but it's a pretty big range for an optical instrument. So I was hoping that I could say, let me measure the velocity of the lines in the blue and measure them in the red. There's a difference in the contrast, those photospheres, and that could be a great indicator. I don't know. Maybe it's for some star. It's not for the sun. On one hand, people have certainly tried using chromatic information. For the M stars, there's some like Teegarden star, at least one other, where I've seen people use, they'll call it a chromatic index. So they basically measure the velocity using lines separated by either order or some other chunk of wavelength range, and then fit some model to how that, at each observation, the velocity is a signal that's correlated with that index giving you how far it is in its wavelength. So for some of the M stars, we have seen that be a useful tool. I'm still optimistic we might be able to do a better job for that for the N stars, but haven't explored that personally beyond the sun. For the sun, we start with a line list that spans the whole way, and we start eliminating things for various reasons. At the end of the day, when you throw histograms, we basically threw out most of the things in the red. It's really sad to me. Like, we collect all that data. It's great data. We are working on trying to make use of it, but it's not being used by the current algorithms that are reaching these 30, 40 centimeters per second. I will say one aspect that I did not talk about today was trying to jointly model the stellar features and the tellurics. So traditionally, you imagine the stellar feature is constant and it's just shifting. Then you can say, well, what if I allow for some stellar variability? Maybe I allow my stellar spectrum to dance. You can also say, what if I allow my telluric spectrum to dance? Treat that as a data-driven model. So we developed a method that could do computation with that, sort of like a very, like an autoencoder type setup. But that worked fairly well. We were kind of pleased. And we said, well, okay, in the infrared, it's struggling, but we don't need to learn about what water lines do from our data. We know that, right? And so what if instead of treating it as a data-driven model for tellurics, what if we build that in? And so Christo Ment has been leading the effort to build in the telluric knowledge so that we retrieve information about the tellurics from the regions of the spectra where we can see it clearly, and then use that to make inferences about the microtelluric contamination, and then use that to improve the ability to measure the velocities in the regions that have only small water lines. So that's paper draft sort of getting started stage. So I hope we'll have a positive story on that. It's been challenging, but making steady progress, and so there may be some value there in trying to use the information in the redder orders where water is strong to know what's happening where water is weak to remove the telluric's influence on the blue part of the spectrum. But right now, most of the information we're getting is coming from the blue part of the spectrum. It's a little annoying because in the old days, we'd have a laser comb that was in the red and didn't go to the blue. The new generation of laser combs can provide calibrators all the way into the blue. They're not as stable. So we're working on the operational side of making that more efficient. But I think, at least for now, we're mostly using lines in the blue. And that was at least half the question, but there might have been another half I've forgotten.
It was basically what wavelength regimes are more or less useful. And I think
Yeah, I think 4,000 to 6,000 is where we're getting 90% of the information in the current models.
So one last question.
I was asked about telluric, so go ahead.
So you talked a lot about studying shape effects on lines on the sun and thinking about how you might apply these to other stars. I have a question about something you might be able to apply to the sun, and we can defer thinking about how you might apply it to other stars for now. Is there anything that might be gained from the ability to be able to resolve the features on the sun spatially, in particular like the distribution of the spots and the faculae, and maybe trying to correlate this with the distribution of elements, and then we can think about how you might do this later for the other stars?
Yeah, so nice question on like, one of the advantages of studying the sun is we have ground truth, we have SDO imaging, we can do magnetograms, and like, could we use that information? So, I mean, I guess you could try to use that information to improve the precision with you treat the sun, as if like, I don't know, magically we'll do that for their star. I kind of have like intentionally not use that information because I don't see it as useful as for other stars. The way I see it helping is not I want to make a model that uses it, but after I've made a model and I'm trying to understand what's really happening, I'd like to then take my predictions and correlate them with what actually happened. So I see there's a blip for this 1 hour. Was that blip due to a magnetic feature? Was it due to granulation? What caused that feature? And so I see the role of the spatially resolved data largely in helping establish confidence in the methods we use that don't use that information as almost our exterior check to make sure either understand why or validate that it's actually working well. So hopefully it'll be useful in that way. We've begun to do it, but it's still early stages for that.
Great, so let's thank Eric one more time. Eric is headed to S, so if you want to ask some questions, you still have time.